In chapter 5, we are going to extend what you learned last year about integration to the exponential function, to functions involving the logarithm, and to trigonometric functions. Let's start with the exponential function. And let's look back at what you learned in the previous chapter. If you are to differentiate this function, what is the result? The result is going to be what you have here on the power of e differentiated, which in this case is just a, whatever a is, times the function over here as is, right? And c, the arbitrary constant, is just differentiates to 0, right? You learned last year that the integral is the opposite of the differentiation. So if you integrate this, then you get that, right? Similarly, these two are equivalent. If you are to integrate this, then you are going to have 1 over a times this differentiated, which is a. So these two a's are going to cut out, and eventually you just have this. So if you integrate it, that's what you get. These two results should be obvious to you at this moment. Anyway, you just have to know them and apply them in whatever questions about integration you'll find in exams. But the concept adjacent to all of this is the same, obviously, as you learned last year. Let's look now at the logarithm. We already learned as well that if you are to differentiate this, the result is going to be what you had inside the logarithm differentiated, in this case, the coefficient of x, a, times 1 over this. So basically, this is what you would get. So if you integrate this, that's what you get. This result is equivalent to that, right? If you are to differentiate this, then you'll have a times, sorry, you are going to have 1 over a times 1 over ax plus b. So these two ways are going to cut out. You just have 1 over ax plus b. If you integrate this, that's what you get, right? Pay attention to one very important detail. The curved brackets over here can only be used if you are completely sure that the values of x are positive. And why is that? If you look at any function of this type, the graph is going to be something like this. It's going to be contained in the first quadrant and in the third quadrant. What does this mean? This means that, as you learned last year as well, if you are to integrate a function, what are essentially you getting? You are getting basically the area between the curve and the x-axis. So if you don't know that the value of x is positive, you might as well get a negative area, and the result of the integration would be negative, right? To ensure that you know how to solve this, you are going to get the modulus function. The modulus function does what? It guarantees that the result that you get after integration of functions such as this one is always positive, and you don't need to worry about if x is positive, negative, or whatever. If you don't have any information about x, the result that you use is just this. Is that, but with a modulus, all right? That's what I have over here. In this case, I just use the function 1 over x to simplify the IDE as subjacent to this, but the concept can be generalized to any function of this type. So if you have any two limits, a and b, whatever they are, this area over here between a and b is going to be equal to minus this area over here between minus b and minus a, right? And to ensure that the magnitude or the value of the area is kept the same, you use the modulus function. All right, that's what you have over here, and you can generalize these results. You can generalize these results for any function and its derivative, as long as the derivative is on top and the function itself is in the denominator of a fraction. Look at what you have over here. Isn't a the outcome of differentiating ax plus b? In this case, you have the natural logarithm of ax plus b If you don't know the value of x, again, in modulus, right? But this can be generalized to any function and its derivative. So the integral of the fraction between the derivative of a function and the function itself is going to be the natural logarithm of the modulus of that function. And similarly, you have this result as well, which is comparable to this one over here. And what do you do with this? You just know the results and you apply them to any question regarding integration, as we are going to see on the questions after. What about trigonometric integration? Again, it's just the opposite of the differentiation. So you just learn how to go from here to here, right? So the integration does the opposite process. So I'm just going over the three that you need to know, but they are basically the same as you learned previously, as you learned to integrate the cosine, the sine, and the tangent.